So, hi everybody. Today's talk is by Henrik Matthiesen, who will talk about new minimal surfaces from shape optimization. Please go ahead.
Thanks a lot. And thanks a lot for the invitation. It's a pleasure to speak here. So first, let me mention that, so this is jointly with two people, but separately. So this is jointly with Anna Siffert from Münster. So that's the closed part, and then the case for surface with boundary is jointly with Romain Petrides, who is from Paris. Okay, so I want to talk about two types of problems, two types of shape optimization problems. So the first one is just basically the eigenvalues of the Laplace on a closed surface. So you say take sigma, a closed surface in this case, and then I have the eigenvalues, but let's focus on the first eigenvalue of the Laplace operator. So that's the first eigenvalue. Okay, so for me, the eigenvalue is so the constant functions, that's lambda 0, and then the first eigenvalue is the first one, which is positive. First eigenvalue of Laplacian. And then, so you want to consider this as a functional of the metric. So consider, so I take the metric G, and then I map it to like this eigenvalue. Okay, now this function is sort of silly because that's not scale invariant, right? You scale the metric, then this scales inversely to that. So I should maybe make the scale invariant. And one way to do that is to multiply by the right power of the area. And in dimension 2, the right power is exactly 1. Okay, and then let's call this thing here, let's define this as lambda 1 bar, sigma g, and this is scale invariant. Okay, so that's the first type of problem. The second one is kind of the same flavor, but for a slightly different operator. So let's say you have sigma, a compact surface. So then I can look at the Dirichlet-Neumann operator. So you can look at the operator T, which takes smooth functions. Oh, I should mention, of course. So the boundary is supposed to be non-empty, also compact and smooth. So takes smooth functions on the boundary and maps them to themselves, and it's given by, well, if you have a function, then you take, first of all, you take its harmonic extension. That's the harmonic extension to all of sigma, and then you take the normal derivative in the outward pointing direction. So okay, and then if you do the analysis, it turns out that this is kind of an essentially self-adjoint first order elliptic pseudo differential operator. So you also have like spectrum, and it's discrete. And so the first eigenvalue of that is called Steklov eigenvalue, first Steklov eigenvalue. So that's the corresponding first eigenvalue, corresponding first, and they are called Steklov eigenvalues. And then you again want to consider this as a function of the metric. So I can again do this thing where I just consider this as, well, I map this to this eigenvalue. Okay, now again, this has the same type of problem. This is not scale invariant. And now the right thing to do here is to multiply by the length of the boundary. So take the length of the boundary. And let's call this thing here, same thing, sigma 1 bar of sigma g. And the power of the length is exactly the right one. So this is again scale invariant. Okay, and it turns out that there are many parallels between these two problems. I'll try to emphasize those, but I'll also try to emphasize some things that are slightly different. So what are the basic type of questions you might want to ask about them? It's just the following. So maybe the most basic one, which is also very classical, is, are those functionals bounded? Oops. So are these bounded functionals? Then maybe you want to ask, if they are bounded, are there maximizers? Are there maximizers, then you might want to ask, is there some sort of rigidity? So is there some rigidity? And then maybe you might ask for kind of the explicit value of this thing on the maximizer. So explicit values of something like, I take the super of all the metrics of this thing here. So where I fixed the surface, so this is now fixed. Oh, so that's of course in the wrong spot here, right? Let's see. So the bar goes over the eigenvalue, not over the metric. This, or same thing for Steklov. Okay. So let's start with the first question. That's very classical, and this goes back to so there's this work by Yang Yao from 1980, which says that if you have, say, a closed surface, then this quantity is bounded purely in terms of the topology of sigma, namely by, okay, so there's 8 pi, and so then they had something, okay, so now the version I'm writing down actually goes back to, so there's some improvement in the constant, which I'll come back to later actually, which says that you can put the genus of sigma plus 3 divided by 2. Okay, so Yang and Yao, so they had like something slightly different here, and this was then, but that's easy to improve once you know what to do. Okay, so this gives you boundedness, and so you have something similar for Steklov. So for Steklov, you have like there's work by Kokarev and then Fraser and Shane, which gives you the same thing. Gives you that sigma 1 bar is at most, and you can put like minimum of 2 gamma plus k, and you can put 8 pi gamma plus 3 divided by 2. Okay, I'm sorry. So here, so gamma, that's the genus, and k is the number of boundary components of sigma, and k is number of boundary components. Okay, so here you have that these functions are bounded, and then so kind of a recurring topic in modern differential geometry is actually this question here. So finding these explicit values. Okay, so let me give you a short history of that problem. Okay, so I think the earliest work is one by Weinstock in '54, where he actually computed this thing for. So he showed that if you look at the case of the disk, then you're always at most the value you have at the flat disk. So that is at most 2 pi. And of course, you know, so this is achieved at the flat disk. So then there's kind of the same thing for the sphere. So that's in 70, which says that if you look at the sphere, then you also get at most the value for the round sphere. And so you also have equality achieved at round sphere. And then here you also have rigidity. So, but that comes much later. So not much later, but a bit later. So rigidity here from the famous paper by Montiel and Ross in '84. Okay, so you see it always takes quite a while to make progress on that. So, and then it took, again, another 14 years. And then there's the famous Li Yao paper on the conformal volume from '84, where they handled the first eigenvalue projective space, which is at most the value of 12 point again. So you have equality on round RP2. And again, rigidity here, you get it from Montiel and Ross. Okay, then it took again another 12 years till Nariashvili did the case of the torus. Also, that was in '96. So he showed that if you go to the 2 torus, so that's the torus, then okay, so the bound is 8 pi squared divided by square root of 3, and equality only on the flat equilateral torus, on flat equilateral torus. Okay, so let me make a remark on his proof. So the way you proved all these other bounds like Weinstock, Hirsch, and Liao was basically that you prove a general bound on the eigenvalue, which you can see to be saturated at some specific metric, right? Like the one for the round sphere, you prove that any metric on the sphere has like this normalized eigenvalue being at most 8 pi, but of course you know it's saturated at the round sphere, so you get that sharp bound. So that's not the way Nadirashvili's proof works. So he proves that there has to be a metric, so maximizing this thing, and then basically so this here so Montiel-Ross kicks in again and tells you that the maximizer has to be flat, at which point Berger, work by Berger gives you the exact value. Okay, so then it took another 10 years for the Klein bottle to be kind of finished off. So there's Al-Sufi, Giacomini, and Zaza in 06. So they did the Klein bottle where I can't even give you the right number because it's connected to like elliptic integrals, but okay. So and then I should mention, so there's a bit of a caveat to this. So actually, to be very precise, Montiel-Ross does not quite handle that because you have to deal with like metrics with certain singularities. So you also need some, so that was only like vigorously carried out very recently. So there's like work by Gianti, Karpukin, and Medvedev from 19. So where they do the Montiel-Ross with sufficiently with less regular metrics that actually cover the metrics you need to conclude these theorems. But that's kind of a technical remark. So then very recently, so Mayatani and Shoda in 17, they proved that if you look at the surface of genus 2, okay, so then you have at most 16 pi. Okay, so note this is exactly the Yang-Yao bound that I stated earlier. So the one which is like 8 pi times genus plus 3 divided by 2, like integer part. So that's the 16 pi. So the thing they actually proved is that this is achieved at some metrics. So is saturated at some metrics. Okay, so this is their actual theorem. So the bound is, oh yeah, I've seen the question, just give me a second. So they just proved that there was kind of a family of metrics that was conjectured to achieve 16 pi. So that was conjectured. So this was conjectured by a bunch of people. So it was Jacobson, Levitin, Nadirashvili, Nigam, and Polterovich. So they had exhibited the candidate that should achieve that 16 pi, but they didn't prove it, and then that was verified by Nayatari and Shoda in 2017. Okay, so the question in the chat is, what do I mean by less regular metrics? So I'll come back to that question in more detail. It is basically metrics with isolated conical singularities. And I'll also try to explain where that comes from. Okay, so there's kind of a story I'm not mentioning here at all, but at least I want to put some name. And that is that, so I've only talked about the first eigenvalue so far, but of course I can ask the very same questions also for higher eigenvalues. And that subject has kind of exploded in the last maybe 5 to 10 years. So a lot of recent results on higher eigenvalues. Okay, and I just, okay, so let me put all the names that you should mention here maybe, and then I'll just tell you what they proved without writing it all down on higher eigenvalues in recent years. Okay, so there is Nadirashvili, Sir, Penskoy, Petrides, Kapukhin, Petrides, Fraser, and Shane. Okay, so let me oh, and I should also mention Giroir. Okay. Okay, so let me mention what we understand that case by now. So we completely understand what's happening on the two-sphere. So we understand the two-sphere, any eigenvalue, and the story here is that, so it started with Nadirashvili doing the second eigenvalue, then it was Nadirashvili and Cyr doing the third, and then it was Nadirashvili, Penskoy, Petrides, and Kapukhin doing any eigenvalue, relying on work by Romain Petrides. Okay, so then so RP2 also any eigenvalue by now, so that was only last year proved by Misha Kapukhin, again relying on that work by Romain Petrides, which is in fact also revisited by Kapukhin, Petrides, Nadirashvili, and Penskoy, I think. And then also the disk any eigenvalue is known, and that is worked by Fraser and Shane and Petrides and Giroir. Okay, but I'll focus mainly on the first eigenvalue for today. Okay, so that's the complete list of things we understand explicitly, like including the numbers. Let me now talk about these other two questions, kind of the questions of existence of maximizers and the kind of rigidity. So it turns out they're very they're like closely connected, and in fact also those results are connected to that. Okay, so question in the chat is that if the maximizers are the same. No, they're not. Let me just draw a picture for the two-sphere. So for the two-sphere k equals 1 is just a round metric, and then for k equals 2, there is no smooth maximizer, but kind of a sharp, kind of basically kind of more singular competitor achieving that thing is just you take two spheres of the same radius and attach them at one point. Okay, and there's no smooth maximizer. And then you just keep going like that. So for k equals 3, you just take 3 spheres of the same radius. Okay. And then RP2, it's slightly more complicated. So RP2 is like, it's one RP2 and then a bunch of spheres, and you have to adjust the radii in kind of the obvious way, if you think about it. Yeah, I will. So this metric is more singular than what isolated conical singularities allow for, and I'll give you I'll try to give you a precise idea of what these singularities are, and those are way more singular. So this here is basically, so in this example here, that's essentially like a one-dimensional singular set, right? Because you collapse a circle. Whereas kind of these conical singularities, I'll be more precise about later, are isolated. Okay. Okay. So now, let me now talk a bit about some sort of this answer to this rigidity question, and so this is kind of the following thing. So if maximizers exist, if maximizers, say for this lambda 1 bar or sigma 1 bar exist, they are induced by certain minimal surfaces, So for so lambda 1 bar, this is minimal surfaces. So minimal, I should emphasize it's only immersions into round spheres. And for the Steklov case, it is free boundary minimal immersions into Euclidean balls. So that's free boundary minimal immersions into Euclidean balls. And so, okay, so I should put names here too. So the closed case, that was kind of, that goes back to Nadirashvili, and then also El-Soufi, oh, I'm sorry, and Elias, and then this is Fraser and Shane. Okay, and in fact, so this connection is kind of pivotal for all results in the subject. So for instance, the way you prove like these results is basically also by studying, like understanding like moduli spaces of like minimal immersions, or more generally harmonic maps into spheres or Euclidean balls. And it turns out that also the existence theory is kind of connected to that. But first of all, let me kind of state the theorem in this direction. So the theorem on the existence part is that. So the first one is that. Okay, so that was finished off by Anna and me last year, but it heavily relies on work by Romain from 5 years earlier. Okay, so and it just says that, well, on any closed surface, for the first eigenvalue, you can solve that maximization problem, and then you get these minimal immersions into spheres. Okay, so let's say let sigma be a closed surface. Then there is a metric G, which is smooth away from finitely many conical singularities. And okay, so I don't want to write this all the time, so let me call this almost smooth. So such that this maximizes, so such that lambda 1 bar, if I take any competitor, is at most this. Bar G for any. Okay, and then you can put like say H being almost smooth or smooth. That doesn't make too much of a difference for any smooth H. So then in particular, they're induced by these minimal immersions into, potentially branched though, into spheres. So these are induced by, so possibly branched. Minimal immersions into spheres. Okay, and let me also make the remark that this type of regularity, so the finitely many cones, that's perhaps optimal. So the explicit maximizer in genus 2 has these types of singularities. Okay, now there might be a miracle, and there might be like another maximizing metric that is like completely smooth, but I mean, how should anyone ever find out? It's totally unclear. Okay, so and then the second theorem is the same thing for Steklov, and so I mean, it looks the exact same, and also the problems look so similar. I will try to emphasize later why it's actually two different theorems and not only one, which happen all at the same time. Oops, okay, so then there's theorem B, which is jointly with Romain from this year. And then again, it relies on like a lot of work done earlier by Romain, in this case from 2015, I think. Okay, so it's the very same result, but for Steklov, there's a subtle difference though. I'll talk about the proofs in a bit. Okay, so let sigma be a compact surface. Let's say the boundary is non-empty, also compact and smooth. So now here's the subtle difference. So then there is a smooth maximizing metric. So then there is G, which is smooth. Okay, so in this case, I don't have these conical singularities. Smooth, such that I maximize. So such that, if you look at the scale invariant guy, then, and I look at this for any competitor, then I'm at most to 1 at G. Okay. All right. And the reason why you can get rid of these singularities here is that so remember how the Steklov eigenvalues is defined. Well, you take a function on the boundary and then you take the harmonic extension into the interior. But now you're in dimension 2, which means that being harmonic doesn't depend on you can change your metric conformally, and that doesn't affect that, right? So in other words, so the metric G is really only in the interior, you can make conformal changes without like affecting anything. And you can basically get rid of those conical singularities in the interior by changing the metric conformally, because these cones are also conformal. Okay, so and then let me state the second part as a separate theorem, because that was not known before. So is that actually you get these new minimal surfaces. Okay, so let's just say let sigma as above. Then there is a free boundary minimal immersion from the surface into some Euclidean ball for some n. Okay, and let me mention that. So now, so then so that theorem as stated is kind of silly, right? Because so one way you could also like prove that theorem is, well, you just take branch covers over the flat disk. Okay, but that's not happening. Okay, so I should put here, so these are not just branch covers over the flat disk, etc. Okay, I mean, another thing that could happen is that, well, maybe you have one interesting examples, but then all the next example are just branch covers over that guy. That also doesn't happen. Okay, and so both these theorems cover basically any topological type of surface. So I mean, could be orientable, could be non-orientable. So strictly speaking, there might be some parts which are not written down anywhere, but it's really minor. I mean, all the arguments are there, so it might only be explicitly written in the orientable case, but it definitely works also in the non-orientable case as well. Okay, so let me mention some previous results here. So previous results are that, so let's say, so first of all, so theorem B, so theorem B, in the case where for surface of genus 0, oh, I want to put K, so i.e. genus 0 and K at least one boundary component. So that was done by Fraser and Shane in, okay, now it's a bit trickier in how you put the years, right? So the paper is only published in 17, but it was in 13, right? So Romain's work from 14 and 15 is an adaptation of their work. So then the, okay, so let me actually give, let's call this here, let's call this free boundary minimal surface. So these free boundary minimal surfaces, so there's a bunch of results using like all sorts of techniques from geometric analysis to construct those. So there's work by, so I'll just put some names. So there's like work by Catover that uses equivariant min-max. Then there's then there's like gluing or desingularization techniques like by Fuller, Pakar, and Solo, Terava, and then also like these techniques by Kapoulias and Weigel. Oh, there's also Kapoulias and Lee, I'm sorry, so Kapoulias and Lee, Kapoulias and Weigel. So these are all kind of these perturbation or more generally like desingularization techniques. And then again, so min-max, there's Colotto, Schultz, oh, it's not alphabetic, right? So Colotto, Franz, Schultz. So now, of course, there's always a trait, and the trait is that, so all of these examples, so all of these are embedded, so ours might not be embedded, and in the free ball, so of codimension 1. Okay, on the other hand, they all come with some sort of restriction of the topology, so but have some restriction on topology. Okay, and typically, so they have either the number of boundary components going to infinity or the genus, but not both at the same time. So for instance, okay. Okay. Okay, so now let me talk a bit about kind of the proofs of these theorems, these maximization problems. So, and let me first of all talk a bit about the closed case, because it's easier to draw pictures. Closed case, so meaning that this is theorem A. So the first ingredient is that you can solve. So I mean, so you want to solve this maximization problem in dimension 2. So you should do the thing you always do. So you split up your metric in the modular space direction and the conformal direction. And then if you fix kind of the conformal class, then this problem had been solved earlier. So that's work by Romain. So, and also independently, Nadirashvili and Cyr. So there's Petrides and also Nadirashvili and Cyr. So they had, I mean, so Nadirashvili and Cyr still had some kind of extra assumption that was then also so they have two independent proofs, but Nadirashvili and Cyr was an extra assumption that Romain could remove. So solved the maximization problem, in a fixed conformal class. Okay, and so let me like give you the proof in a nutshell. I'm totally under exaggerating like concerning the difficulty. So the thing you exploit is that in the case where you like have maximized over all the metrics, they are connected to these minimal surfaces. Now, if you fix the conformal class, you will still have something similar, and that thing is harmonic maps. Okay, so now you might not get like an isometric, you might not get a minimal immersion, but you still get a harmonic map. And now the idea is to, instead of looking at the full problem, to look at like some relaxed or like compactified problem for which it's easy to find maximizers, and you still have some approximate version of that harmonic map equation. And then try to use those approximate harmonic maps to pass to the limit. So the key thing to rule out in a way is bubbling, but you can do that by an assumption on the eigenvalue. Okay, so that relies, just in a nutshell, that relies on a relaxed problem plus connection to, and then let me put here, so for the full problem you would get harmonic maps, but then for the relaxed problem you get some sort of approximate harmonic maps. And then, so basically, so there is assumption on the eigenvalue on, so this rules out bubbling. Okay, and so then actually, so this comes with some extra information. It comes with the following extra information, and that tells you also where these conical singularities come from. So what you get is that, so the maximizing metric, so you get a maximizing metric. And let me already put kind of a sequence here. So Gj, so in its own conformal class, as follows. So you recover this metric by the energy density of a harmonic map. So this thing here is a harmonic map to some sphere. So that's harmonic. And this is the hyperbolic metric in the conformal class. Hyperbolic metric in that conformal class. Okay. So again, conformal invariance is important here, right? Because the notion of being a harmonic map in that case, conformally invariant. So that works with taking the hyperbolic metric there. And so then if you take like, if you, for the problem on the, like among all the metrics, if you pick your maximizing sequence of that type, then you have broken up into these two parts, namely you have this harmonic map part here, and you have this modular space part here. Now the thing is that still this remark applies as well. So still in the harmonic direction, you don't have a big problem because still you don't have a problem with bubbling. Okay, so for the phi, so for the nabla phi j, oh, there's the squared part. So still okay because no bubbling occurs. Okay, so the part to worry about is kind of this directional moduli space. But now you know what degenerations look like, right? So potential degenerations. So degenerations for this conformal factor is something like, so maybe I start out like this, and then I have a curve that becomes shorter and shorter and shorter. So maybe I have like this. Right, and then the limit I pinch off. So in the limit I'm something like okay. And then you can actually, again, use kind of the conformal invariance, and you look at the cusp compactification of this guy here, and then you could show the following. You can show that this forces the following. Okay, so now I have to introduce some notation. So notation is that, oh, let's give a name to this thing. So that's the sup in genus gamma. Sup G lambda 1 bar. So that is genus gamma. Okay, so now this degeneration would force that if you look at the if you just look at the at this quantity, right? So let's say this was my guy of genus gamma, right? So my sequence of metrics is assumed to achieve that. So in the limit I get that. But on the other hand, I have this competitor here, right? Okay, which is non-compact, but then you look at the cusp compactification. So you would get that this goes below the genus 1 below. Okay, so in other words, all you have to do to rule that out is that, so this is ruled out, if you have here the strict inequality that way. So if you can prove that when you increase the genus, that quantity always strictly increases, you can rule out these degenerations and you'll be fine. Okay, oh, so now I announced that, but I didn't explain that, right? So if you go back up here, so that tells you where these conical singularities come from, because it comes from the vanishing set of the gradient of that harmonic map. And those give you precisely those conical singularities. Okay. So then for the case with boundary, it's kind of the same picture. It only becomes harder to draw. So similarly for Steklov eigenvalue, so you have more potential degenerations. So e.g. Need strict monotonicity in number of boundary components and the genus. Okay, I'm oversimplifying here a bit. So if you know about this, so there's one more degeneration which is important. It could happen that you lose one in the genus, but you gain one boundary component. Okay, you also have to take care of that one. Okay, so and then so we just prove kind of more general gluing theorems, giving you exactly these results. So let me state those. So the first one is theorem A prime. So it just says that you can always do that. I mean, if I have a surface with a given metric, and then I move to like genus 1 higher, then I can make this thing strictly increasing. So let's say you start with something closed, and it's almost smooth. And then let's just say you have another surface, which is obtained from sigma by attaching a cylinder, or for the non-orientable case, you also have to take care of cross caps or a cross cap. So then you can find a metric that does the job. So then there is G prime on sigma prime such that you strictly increase. So such that lambda 1, so bar, so I strictly go up. Bar prime, G prime. Okay. So then, so let me draw a picture. So the picture, I mean, so I start with some surface sigma. So that's maybe my surface sigma. And then sigma prime is something where you take like 2 points, then you remove like tiny disks near that, and then you like attach like something like this, right? Okay.
So there is a question in the chat.
Yeah, so let me just read it. I would have to think about that. I don't know. I would have to think about it. That's all I can say about it. I'm sorry. Okay. So then the second one is the same thing, but for Steklov, and let's again phrase this in this kind of more general way. So let's say you start with so compact boundary non-empty. Then you have sigma prime from sigma by attaching a rectangle. So I'll draw a picture in a second. A rectangle. Then there is some metric G prime on sigma prime such that again you strictly increase. Okay, so what does so what is happening here? So you have some surface which is maybe like this, right? So then maybe I have genus, and then the thing I do is I just pick 2 points in the boundary, like here and here, and then I attach a rectangle like that. So maybe like this. Can I draw that? I hope so. Right. So this is attaching a rectangle, right? Okay. So that's then your new surface. And now, of course, here I have like, so I was mentioning a second ago that there are kind of, in the case with boundary, that there are like many different ways you could have these degenerations. So now, of course, why is that handled by the single statement? Well, because you also have like many options how to like glue that, right? So for instance, I have these 2 points here, so I could choose them in the same boundary component or in different boundary components. So then also I have, so the thing I have is the orientation in which I glue. Like I have the orientation here and here. I could choose that compatible or not, right? So resulting in something, again, orientable or non-orientable. And by like using all these different options, you get all the monotonicity results that you need to actually conclude the theorem. Okay, so let me first of all give you an idea. So you can actually use that result beyond just getting the existence statement, but also to gain some insight in the geometry of those minimal immersions. So let me explain this because I think it's kind of neat. So corollary, and it's way more general than this. So let me just state kind of a very simplified version of the actual result. So for infinitely many gammas, no maximizing metrics. So on the surface of genus gamma, so of course for lambda 1 bar, is induced by a branch cover over the round sphere. Okay, and it turns out that this is actually very simple to prove because so if say if it is induced by such a cover, then for this quantity, so well, okay, it's a branch cover of the 2-sphere by first eigenfunctions. I should have mentioned that it's all by first eigenfunctions all the time. So the eigenvalue is 2, but then you have the area formula, which tells you, which just computes to you the area in terms of the degree of the covering. But the degree of the covering is an integer, right? So you see that this is quantified by 8 pi times some integer. So in k gamma, that's an integer. But then, so you know that, so if that also happens, so if also on the next one, well then of course you know that this one here, so there also has to be 8 pi times another integer. But from our theorem, you need to know that you strictly jump, right? But then you jump at least 8 pi. Okay, you see that, so A prime, so theorem A prime. In this case, so theorem A prime implies that this integer here is at least that integer plus 1. Okay, but now you see if this happens over and over again, then, okay, so if this keeps happening, then you would get that this quantity here grows at least like 8 pi times the genus. But Yang Yao, I mean, the improvement by Zufing Elias tells it's at most 4 pi. Okay, but it's at most 4 pi times the genus. So that can happen. And the same argument actually gives you kind of, you can count the number of times that happens, and you can also prove like an estimate for that number and stuff. Okay, so let me use the remaining time to convince you that proving kind of these gluing theorems is hard and how you cannot prove them. So how not to prove theorem A prime and theorem B prime. And then if there's time left, I might indicate how you actually can prove them. Okay, so let's look at kind of maybe the first idea you might have, and that is the following. So you start with surface sigma, so which is here. And then I associate a new surface to that, which we call sigma epsilon sub 8, which is as follows. Okay, so it's the original surface. And then I attach a cylinder here, so which we call C epsilon 8, and let's just take kind of the simplest geometry you could imagine for that. So let's just take kind of the flat product metric. So you take, this is just a sphere of radius epsilon times an interval of length 8. Okay, and then of course what you easily check is that if you compute the area of this guy, then this is the area of your surface, then you gain in term on scale epsilon, and then, okay, you have removed this sphere of radius epsilon, but the area of that is quadratic, so you just have capital O of epsilon squared. Okay, so you have some gain in the area, so now the thing you try to do is you try to find out how the eigenvalue behaves and hope that kind of this gain here compensates the potential loss on the eigenvalue. Okay, so eigenvalues and targets. Okay, so let me first of all mention that so this is kind of something that has been considered for a while. So this has been considered by was introduced by Colette Arnay in I think 90, and then it was also kind of used in the context of these problems by Qualbois and Sophie. I think it's 03. Okay, and let me make some simplifying assumptions here. So assume, for simplicity, that the first eigenvalue of that surface is simple. Okay, it just illustrates the difficulties. It's doesn't matter too much. And then also something that's important is that, so let's say I have these points here where I attach. So this is this point x0, and then I have this point here, x1. So then here, so the multiplicity is 1, so I get a kind of the associated eigenfunction. So associated eigenfunction. And let's assume that it has the following. So assume so also assume that phi naught of x0 plus phi naught of x1 does not vanish. Okay, now of course you might tell me that's silly, right? Because it is. basically, if I make this assumption here that I have multiplicity 1, of course I can just adjust the points x0 and x1 to always make this thing 0. Okay. The point is that if you're in the case where you have, like, say, a maximizer, that's exactly the situation where you might not be able to like get this to be equal to 0 for any eigenfunction. But then there's still like only like a single eigenfunction basically not having that, like up to, you know, choosing an orthogonal basis. And all the difficulties occurring in that case are just illustrated in that toy example, which is why you can basically make those assumptions. Okay, so then here is kind of the eigenvalue asymptotics in that case. So which I did with Anna in 2018. And I'll draw a picture to explain that. So we have the following asymptotics for the first eigenvalue of this surface sigma epsilon h. Okay, so the picture is as follows. So I have this parameter h, and then let's put here the square root of the eigenvalue. Then what's the picture and the limit? The picture and the limit is that I have somewhere here, I have the square root of the eigenvalue of sigma, and then I have the Dirichlet eigenvalue. So this is the same thing as lambda 0 of this cylindrical part, which collapses, and the square root of that, which I think is pi divided by 8. I might be a bit off, but okay, something like that. So now, how do the eigenvalues of the surface look like? They look as follows. So the first eigenvalue looks like this. And the second eigenvalue looks like this. Okay, so this is lambda 2 of this. And this is lambda 1 of that. Now, of course, something that matters is the exact scales on which this is happening. So, okay, I haven't used black in here, right? So and the thing is that this here, this is on scale epsilon to the 1/2. Okay, so now let me make, okay, so one more thing. Let's call, so this parameter here, h star. Okay, okay, and the gap here, oh, it should be black. So the gap here, that is at most epsilon log 1 of epsilon. Okay, so now let me make a few remarks on that. So the first remark is that, well, so of course this term here looks better than this, but we don't expect to kind of prove this theorem like using those parameters here. So why is that? Because of course the theorem has to rely in an essential way that you change the topology, right? Because say if I started a maximizer and I don't change the topology, I can't go up. So really the construction should observe the change in topology in an essential way. And it turns out that if you look at kind of the precise computations, that here in this regime, you don't really see that, okay? But so where you see it is near this parameter h sub star, okay? So here, but for these parameters, so for these here, so we don't see the change in topology on the spectral level. So you shouldn't expect to get the result in that regime anyways. So you should work near to h star, but there you lose, right? Because here you go down by this much. So you go down by epsilon to the 1/2. The gain in the area was only on scale epsilon, so you lose. Okay, so you see that if you compute the normalized quantity, this goes strictly down for h near h star. Maybe I should put like 8 epsilon. So in fact, I mean, there's a formula for the eigenvalue and stuff. Okay. But there's something more important here. The more important thing is to understand why this happens. So the origin of the scale epsilon to the 1/2 is the following. Let's say you take psi epsilon h and L2 normalized Dirichlet eigenfunction on the collapsing part. So lambda 0 of c epsilon h eigenfunction. Okay, then you just see if you compute the boundary integral of the normal derivative. So I've computed this. So then this is on that scale. Okay, and this is where this ultimately comes from. So this is so maybe let me say this. So okay, let me redraw the picture. So the picture is something like, okay, maybe so think about it like this. So I have my surface here, and then maybe here I have kind of attached this cylindrical part, and it's going like somewhere. And then I have this eigenfunction, and if you look at the part where I glue, so here, kind of it propagates into that. So the eigenfunction from this part here kind of wants to propagate a term on that scale into the thick part. Okay, and the way it propagates that, so this propagation here, so propagates via the kernel of this operator. Now the thing how this assumption comes in is, remember I had this assumption that this does not vanish, is that of course this operator is not invertible for all lambdas. If I hit exactly the first eigenvalue, it's not invertible. So I can only invert up to the projection of the kernel, which is exactly where this comes in. Okay. So now, so what's the lesson to take away from that? If you ever want to have a construction along those lines that gives you the positive results, then you have to do better here. But that means basically you have to glue in something with that starts seeing some continuous spectrum. Okay, so basically you get that a construction along those lines, giving theorem A prime and B prime needs to use a collapsing part, developing a continuous spectrum. Okay, let me just tell you what we use, and then I'll stop. So in the closed case, you just use the following. So just use a truncated hyperbolic cusp, or truncated, let me say, yeah, let me put hyperbolic cusp. So it's just something which looks like this. Okay, the drawing is not very good. I mean, this is like something like, yeah, per half plane mod z goes to z plus 1, and then maybe intersect with the points that are at least, or let's put z times to z plus epsilon, and then I intersect with points which are at most, so the y coordinate is at most y. Okay, so this is height 1 and r. So for then r, which will be r of epsilon, going to plus infinity appropriately. Okay, and then again, so in the case I just explained a bit, there was this parameter 8. So we replace the parameter 8 by parameter kappa, which is just, okay, so now I wrote down exactly the hyperbolic cusp. I can also use like constant negative curvature kappa. And then that's the kind of the replacement for that. Okay, and in the Steklov case, so there's use the following set. I mean, again, appropriately scaled. So but it's something which is modeled on the following. So you have something which looks like this. So it's like R, this is 1. So this is like, that's the points in the plane where, let's see, so you have something like minus y squared divided by 2 is at most, x is at most y squared divided by 2, and r is at most y is at most 1. Okay. And again, then you have to scale appropriately and like introduce some parameter here. I mean, so you would put like a parameter here which replaces the curvature. So now you can imagine that actually then proving things will be horribly technical, because you have like this accumulating number of eigenvalues that will give you like a headache. And also now let me make this final remark. So why is it 2 theorems, not just 1? So that remark is that if you go to this case here, then you can compute a lot of things explicitly, because you have separation of variables, right? You have this continuous symmetry, and then by separation of variables, you can like compute a whole bunch of things just explicitly by hand. I don't think you can do this here. So we tried to like do things to some degree for some time. We didn't get anywhere. So you have to develop more robust techniques that basically avoid needing those explicit computations. And that's why it's not just one theorem. So I think by now you could actually take the arguments from the Steklov case and do the Laplace case along those lines. But initially that was not possible. Okay, so thanks for your attention, and I'll stop here.
All right. Thank you very much.